Welcome to Stochastic Processes and Queuing Theory. Today we are going to explore waiting time distributions, a fascinating and highly practical topic that helps us predict exactly how long a customer will spend in a system. Whether you are managing a hospital emergency room, a bank, or a computer network, understanding these mathematical distributions is the key to ensuring smooth operations and keeping wait times under control. Let us dive in and see how we can model these everyday situations. To begin, let us think about a fast food drive-through. The total time you spend from arrival to departure is the waiting time in the system, denoted by W. But the time you spend just sitting in line before ordering is the waiting time in the queue, denoted by WQ. Because arrivals and service times are random, both W and WQ are random variables. We use cumulative distribution functions to find the exact probability of waiting less than a specific target time. Now that we understand what these variables represent, let us look at how they behave in a standard single server queue, known mathematically as the MM1 model. We assume the system has reached a steady state, which is a condition where the system has been running long enough that its overall behavior and probabilities have stabilized and no longer change with time. When a new customer arrives, they will find a certain number of existing customers, let us call it N, already there. The probability of finding exactly N customers depends entirely on the utilization factor, rho, which is simply the arrival rate divided by the service rate. This brings us to the crucial formula for the waiting time distribution in the system. This equation calculates the exact probability that a customer's total time, W, will be less than or equal to a specific target time, T. The symbol rho is the utilization factor and mu is the service rate. Notice how the variables interact. As the allowed target time t increases, the negative exponent grows larger, making the subtracted term smaller, which pushes the total probability closer and closer to 100%. Conversely, if the system is heavily congested and rho gets very close to 1, the exponent becomes very small, meaning the probability of a short wait drops drastically. Before we move on, let us see this with a concrete example. A bank teller serves 10 customers per hour, and 6 customers arrive per hour. We want to find the probability that a customer spends less than 30 minutes, or 0.5 hours, in the bank. First, we calculate the utilization factor by dividing the arrival rate of 6 by the service rate of 10, giving us 0.6. Since this is less than 1, the system is stable. Next, we state our cumulative distribution formula. Continuing with our calculation, we substitute our known values into the exponent. We plug in 0.6 for rho, 10 for mu, and 0.5 for t. Simplifying the terms inside the exponent, we subtract 0.6 from 1 to get 0.4 and multiply 10 by 0.5 to get 5. Multiplying these gives a clean negative 2. Evaluating 1 minus e to the negative 2 gives approximately 0.8647. This means there is an 86.47% chance a customer completes their visit in under 30 minutes. Now that we have used this formula successfully, let us understand where it comes from conceptually. We start by finding the probability that an arriving customer finds exactly n people ahead of them, which is 1 minus rho times rho to the power of n. If the customer finds n people ahead of them, they must wait for all of those people to finish their service, plus they must wait for their own service to be completed. This means the total time spent in the system is the sum of n plus 1 individual exponential service times. In probability theory, the sum of exponential variables follow a special pattern called an Erlang distribution. We multiply the probability of finding n customers by this Erlang distribution and sum it up for all possible values of n from 0 to infinity. This massive infinite sum looks incredibly intimidating, but we can simplify it significantly. By using the mathematical properties of infinite series, especially the Taylor series expansion for the exponential function, the complex terms cancel out beautifully. We are left with a much smaller, cleaner expression for the probability density function. This mathematical reduction is elegant because it proves that the total waiting time in an MM1 system is itself exponentially distributed with a modified rate parameter of mu times 1 minus rho. This continuous curve represents the exact likelihood of the waiting time being exactly t seconds, which sets us up perfectly for the final step of our derivation. Finally, in real-life applications, we rarely ask for the probability of waiting exactly t seconds. Instead, we want to know the probability of waiting less than or equal to t seconds. To find this cumulative distribution function, we must integrate our density function with respect to a dummy variable x from a starting time of 0 up to our target time t. Integrating an exponential function is straightforward, as the constant multiplier in the exponent drops down to the denominator and cancels out the constants in front. When we evaluate this integral at the upper limit t and subtract the value at the lower limit 0, we arrive at a final, highly useful formula for the system waiting time. So, we have proven how system time works. This brings us to the waiting time in the queue, WQ. The biggest difference here is that a customer might not have to wait in the queue at all. If a customer arrives and the system is completely empty, their queue waiting time is exactly 0. The probability of experiencing 0 wait time is simply 1 minus the utilization factor, rho. Because there is a massive spike in probability exactly at 0, the queue time distribution is a mixed distribution. By adjusting our previous integration to account for this jump at 0, we arrive at the cumulative distribution for the queue time. This formula gives the probability that a customer's wait time in the queue is less than or equal to t. Notice that it looks almost identical to the system time formula, but the exponential term is multiplied by rho. This makes logical sense because if we plug in a time of 0, the exponential term becomes 1 and the formula correctly outputs 1 minus rho, which is the chance of not waiting at all. Let us apply this new formula to a tech support call center. Calls arrive at a rate of 8 per hour and the technician resolves 12 calls per hour. We need to find the probability that a caller waits more than 15 minutes or 0.25 hours on hold. First, we calculate the utilization factor by dividing 8 by 12, which simplifies to 2/3. Since this is less than 1, the queue is stable. We then state our cumulative distribution formula for the queue time. Continuing our calculation, we substitute our calculated utilization factor of 2/3, the service rate of 12, and the target time of 0.25 hours into the equation. We begin simplifying the complex terms inside the exponent. 1 minus 2/3 leaves us with exactly 1/3. Multiplying the service rate of 12 by the time of 1/4 gives us 3. The exponent simplifies perfectly to -1 after multiplying 1/3 by 3. This step-by-step reduction prevents calculator errors. Now we evaluate the simplified expression. The exponential term gives roughly 0.3679. Multiplying this by 2/3 and subtracting from 1 yields approximately 0.7547. This means there is a 75.47% chance a caller waits 15 minutes or less. However, the original question asked for the exact opposite scenario. By subtracting our previous result from 1, we find there is a 24.53% chance a caller will be stuck on hold for more than 15 minutes. To truly understand these formulas, let us look at them visually. This graph plots the cumulative distribution functions for both system time and queue time. The horizontal axis represents the target time and the vertical axis represents the probability. Notice the curve for system time, W, starts exactly at 0 because it is impossible to spend 0 total time in the system. However, the curve for Q time, WQ, has a sudden vertical jump right at the start, up to the value of 1 minus rho. This perfectly illustrates the probability of not having to wait in line at all. Now that we have seen the math and the graphs, why does this matter? In the real world, businesses do not just promise average results. They sign service level agreements, which are strict legal contracts guaranteeing performance. For example, an emergency room cannot just rely on an average wait time. They need to guarantee that 99% of critical patients are seen in under 5 minutes. By using these exact waiting time distribution formulas, managers can calculate precisely how many servers or doctors they need to meet these strict guarantees. Let us summarize what we have learned. We discovered that waiting time provides a complete probabilistic picture of a customer's experience. By separating the total time in the system from the time spent purely in the queue, we can pinpoint exactly where delays occur. We derived the continuous exponential distribution for system time and the mixed distribution for queue time. Using these cumulative distribution formulas transforms queuing theory from a theoretical math exercise into a powerful practical tool for designing efficient real-world services. You now have the tools to analyze any waiting line.